Presented by Caltech.
In the 1950s, computers looked like this. All of these racks back here are filled with electronic circuits. You can see the edges of them here. And when there was a problem, it was usually that the hardware had failed. And we debugged it with an oscilloscope, which you can see here. Well, by the time we got to the 1960s, things had cleaned up a little. We had better devices for talking to the computer, and there weren't electronics hanging out where we had to measure them with oscilloscopes. But it's still a huge room filled with hardware that's generating heat, special air conditioning, most of a floor of a building to house one computer. I don't have to remind you that you now have with you at all times a computer that's thousands of times faster than this. And it's a small part of what's in here. It's on one chip. What was inside the 50s computer were modules that looked something like that. They had active switching elements, which were vacuum tubes, and then they had other elements. Here are resistors, here's the capacitors. This pair of vacuum tubes and the stuff that's underneath it were one logic function, an AND gate or an OR gate or something like that. There was a big step in that general time frame that's shown here. We went from having to wire all those things by hand. You can see somebody had to hook these wires and these things together and solder each one by hand. It was a very inefficient production process. That got streamlined when we went to printed circuit boards like this one. You can see the sockets for the vacuum tubes got soldered on the circuit board, and resistors and capacitors got soldered on the circuit board. So all the wiring was done by these little traces here. You can see the little silver traces. The wires were now on the surface of the circuit board. It was a huge improvement in not only production cost, but reliability. Then there was another huge thing that happened in the 60s. Toward the end of the 60s, instead of using vacuum tubes, we had transistors, like the little black ones there and the little white cans here. They're switching elements just like vacuum tubes, but they're now in little tiny cans, and they don't generate near as much heat, and they're much more reliable. In 1959, there was a huge invention. Bob Noyce figured out how to hook transistors together on the same piece of silicon. The integrated circuit was born, and here's one right down here. The simple logic functions that are this part of the circuit board, these two transistors and the stuff that went with them, these two vacuum tubes and the stuff that went with them, these two vacuum tubes and the stuff that went with them. Each of those little regions are an elementary logic function. This is a single transistor here. The scale, that's about the size of the head of a pin, that whole piece of silicon. It's square, but it's about that size. This is the first integrated circuit. You'll see it's about the same size, not very much bigger, but it has a number of transistors in it. And this is one of those simple logic functions. And every year, we got more and more transistors as people figured out how you can make a more complicated function that still doesn't have too many wires that come off. So people started thinking in terms of modules that did functions like the logic functions instead of individual transistors. It's a big change in the way we thought about things. About the time that this integrated circuit was made, it's around 1965, Gordon Moore had been watching what was happening, and he made a plot of the number of transistors on a single piece of silicon as a function of the year. And here we are in 65, and we're up here somewhere. And then he extrapolated the plot all the way out. And he said, these things are going exponentially. At Caltech, we started working on just how small those MOS devices they were using on their integrated circuits could get before they started not working so well anymore. And we came to some really remarkable conclusions. This was in 1971, and we said that you could get 10 to the 8th transistors per square centimeter, and the chips would still work. There was a lot of debate about that, because that was a long way from where we were. So the more argument you get, the more likely it is for someone to hear about it that's going to think about it carefully. Well, people started thinking about it carefully in those days, and this is what happened. We were back here in 1971 with a few hundred devices per square millimeter now, and we had said that it would be possible to make things with 10 to the 8th per square centimeter at 10 to the 6th per square millimeter. So we would be able to make things up here. So we were more than 30 years ahead in this prediction. And what it's led to is Moore's Law, which was a combination of the compelling case that Gordon had made that if you're able to make more and more transistors on a chip, it will bring down the cost of computing in a remarkable way. And it certainly has. They have to have two things for a revolution like this to happen. The first is people have to believe it's physically possible. And second, they have to believe it's a big payoff if they get it done. And in this case, both things were true. And we've got our modern information technology to show for it.